Hi everyone, my name is Arina Ujevco and I'm an undergraduate thesis student in the Coffey lab for audition sleep and plasticity in the psychology department. My summer project, which became my thesis, pertained to the effect of sound on sleep spindles. Aging is an unavoidable process in our life. The experience of becoming older brings us cherished memories, while at the same time doing the exact opposite, worsening our memory capacities. A decline in memory is present not only in pathological, but healthy aging as well. Thus, it is important to understand some mechanisms behind this deterioration and explore possible solutions. The answers to improving memory as we age could lie in our sleep. Throughout the day, the cells in our brain, named neurons, communicate between themselves to make sense of the world around us. The communication between cells is what makes our movements, thoughts, feelings, and overall everything that makes us who we are possible. Neurons talk as humans would, but instead of language, the cells use chemical signals sent from one neuron to another. These chemical signals are triggered by electrical activity, which we can visually observe using different systems, such as an electroencephalogram. Memory consolidation is also a result of communication between our brain cells, which is important to this study. But what does memory consolidation really mean? Well, it is when a memory is formed, it is then stored into short-term memory. Then later, it is transferred into long-term memory. It was found that our sleep plays a role in the transfer between short-term memory to long-term memory. Our sleep is divided into two types: non-rapid eye movement, which is more prominent at the beginning of our night, and it consists of light and deep sleep. The rapid eye movement sleep is more prominent at the end of our night, and it is usually when we would experience elaborate and bizarre dreams. The non-rapid eye movement can be further divided into stages that are characterized by different cell communication. Recall that neurons make use of electrical signals. We can observe these in an electroencephalogram output. Here are electroencephalogram outputs for the second and third stages of the non-rapid eye movement sleep. On them, we can see the electrical signals used by neurons for their communication. These signals differ in their frequency, which is defined as the number of cycles a wave completes per second. In other words, the communication between neurons in our sleep cause waves seen in these outputs. I'm showing these two stages because they are particularly important for our memory consolidation. During the second stage, sleep spindles can be observed, which are bursts of electrical activity between 11 to 16 cycles per second. A second player in the memory consolidation process are slow waves, which can be seen here. As the name suggests, they are slower than sleep spindles. These are activity between 0.5 to 1.5 cycles per second. During the second stage, a higher proportion of sleep spindles is present, whereas in the third stage, more slow waves occur. But sleep spindles and slow waves are present in both. How do sleep spindles fit in the memory consolidation process? Let's take, for example, a task such as studying, which triggers the communication of neurons across different brain regions. These brain regions are set to then activate as they work to process the information in front of us, to understand what we see, what we read, and the meaning of it. The activation of brain regions represents the formation of new memories, similarly to a video being recorded. This recording will be stored in the back of our minds, accessible in the short-term storage for the rest of the day. During sleep, sleep spindles come into play. Spindles will help neurons access the recording of the memory, and then the neurons will replay the memories from the day. The replay itself is a critical part of the memory transfer process from short-term to long-term use. A third level of complexity is added to sleep spindles and slow waves in the memory consolidation process. However, it is beyond the scope of this presentation. Let's focus on slow waves for a bit. Slow waves are a result of specific patterns of communications between many neurons in our brain. These patterns are the slow waves, and they're responsible for the generation of sleep spindles in the thalamus. Once generated, sleep spindles reactivate new memories, as we saw on the previous slide. These memories will travel from the hippocampus, which holds them in short-term storage, to the relevant brain areas for long-term storage. As you can see, a coordination between slow waves and sleep spindles is important for the memory consolidation process. Sleep spindles and slow waves can appear together at a synchronized time. The optimal timing between sleep spindles and slow waves is thought to be the rising part of the slow wave. As you can see in the second graph, participants in studies that had more sleep spindles appear at this optimal timing with slow waves had also higher retention scores. Let's turn to a study that has compared younger and older adults' timing between slow waves and sleep spindles and memory performance. The participants were asked to perform a learning task, sleep for one night, and then complete a memory test in the morning based on the learning task. It was found that younger adults displayed the optimal timing between sleep spindles and slow waves, shown in red, compared to older adults who had the two electrical signals not optimally timed, shown in blue. Further, in addition to not having the right timing between slow waves and sleep spindles, older adults also performed worse on the memory recall test compared to younger adults. Consequently, this study is an example of how the timing of slow waves and sleep spindles seems to have a role in the deterioration of memory storage processes as we age. Now, if we can manipulate spindles and slow waves, maybe we can restore the optimal timing between them that is found to be important to memory and that decreases with age. By manipulating spindles, we can also better understand and possibly enhance them. A solution to improve the fate of memory processes in older adults could be actually as easy as listening to sounds during sleep. Researchers have shown that participants who listen to sound timed to the rising phase of the slow waves during sleep and remembered more of the learning task the morning after than those participants who did not listen to sound timed to slow waves. If slow waves can be influenced by sound, perhaps sleep spindles can as well. We also know that the rising phase of the slow wave is particularly sensitive to stimulation using sound, so maybe the same logic follows in sleep spindles. This brings us to the current study that has developed during the summer. We have asked ourselves if sound will influence the amplitude of sleep spindles after stimulation. In other words, can a sound presented to sleep spindles influence how high or how low a wave can go from the 0 point? And further, if this effect exists, will it differ based to which part of the spindles the sound will be presented to? So far, 4 neurologically healthy participants were recruited, with a mean age of 25.25 years and a sample which consisted of 1 female. The participants have received the equipment at their home address. Then they were asked to install and sleep with the equipment for a total of 5 nights to get an adequate number of sleep spindles for the analysis. This is the at-home electroencephalogram device used for recording brain electrical activity and to output a stimulation. Half of the detected waves were stimulated using sound, a 40 millisecond ping noise at 55 decibels, and the remaining half of the waves were marked for later analysis. But the brain was not stimulated using sound, which is the sham condition. The system was programmed to detect or wait for a slow wave to come along, give the sound or mark the wave with no sound, and then later during the analysis, we figured out if the stimulation hit sleep spindles and which part of the spindles it hit. To approach our research questions, the sleep spindles were compared between those that have been presented with a sound to those that were not. To determine the effect of sound on spindle's amplitude, we have compared the power of the EEG spindle signal 1 second following brain stimulation. In color are all of the sleep spindles detected during a night of one participant, and in black is the average of the colored signals. Here you can see data points on the x-axis, where 500 points represent 1 second, and on the y-axis, the amplitude is shown in microvolts. To represent amplitude following stimulation, average root mean square values of the signal were used. Here you can see the statistical analysis done for the first research question, does sound influence sleep spindles amplitude? A non-parametric alternative to an independent samples t-test was used for the statistical analysis, the Mann-Whitney U-test. Only the first participant had a statistically significant effect on the root mean square values of sleep spindles when compared to the sham condition, meaning that in the first participant, sound had an increase in the amplitude value of the sleep spindle up to 1 second post-stimulation. The other 3 analyses for the 3 other participants did not have statistically significant results, and that indicates that sound did not have an effect on sleep spindles' amplitude. So far, to draw conclusions, a higher sample is needed, and we will continue recording participants. But a trend seems to be emerging from the data collected so far of a possible influence of sound on sleep spindles' amplitude. If presenting sounds reveals to be a way to stimulate sleep spindles, in addition to slow waves, the start or duration of the electrical signals could be influenced. The next step would be to influence the timing between them by stimulating both waves. Thus, a resynchronization of the two would be possible when needed, such as in the case of older adults when the signals are not optimally timed. The repair timing might be the solution to improve recall for older adults, which takes an important role in our everyday lives. Thank you very much.